Okay, so now we're in chapter 3, which is all about probability theory. Recall from the first lecture that there were two types of statistics, descriptive statistics and inferential statistics. Well, we just finished looking at descriptive statistics in chapter 2. Now in chapters 3, 4, and 5, we're going to be looking at some probability theory, which is necessary for us to move into inferential statistics in chapter 6. So the first thing we need to do is just look at some basic concepts and terminology of probability. So the first thing is the probability experiment. The probability experiment is the action or the trial which does result in a specific result. So suppose the action is tossing a coin or rolling the die. The outcome is the result. So the outcome could be the die lands on a 2 or the coin lands on heads. That's the outcome or the result. The sample space is a set of all possible outcomes of a probability experiment. The sample space for the probability experiment that consists of tossing a coin is heads or tails. The sample space for the probability experiment rolling a six-sided die is 1, 2, 3, 4, 5, and 6. The event is what we're looking for, and it can consist of one or more of the outcomes in the sample space. So for example, suppose our probability experiment is roll a die. Our outcome is a 3. The sample space is the 1, 2, 3, 4, 5, and 6. And suppose the event is the die is even, which consists of the outcomes 2, 4, and 6. Let's identify the sample space. We're going to toss a coin and then roll a six-sided die. All right, so we can look at this tree diagram to see, first we toss the coin and it lands on either heads or tails. Then we roll the die and it lands on 1, 2, 3, 4, 5, and 6. So the sample space has 12 outcomes, which consists of H1, H2, H3, all the way down to T6. A simple event is an event that consists of only a single outcome. For example, tossing a coin and landing on heads and rolling the die, and it lands on 3. But an event that consists of more than one outcome is not simple. For example, tossing a head and rolling an even number consists of the outcomes H2, H4, and H6. So this event is not simple, whereas this event is a simple event. Let's determine whether the event is simple or not. We roll a six-sided die and we want to have it land on at least a 4. Well, the outcomes consist of 4, 5, or 6, so it is not simple. Next, let's look at what's known as the fundamental counting principle. If you can do one event in m different ways and a second event in n different ways, then the number of ways that the two events can occur in sequence is m times n. And this can be extended for as many events as you need. For example, suppose you're going to go out and buy a new car, and there's 3 car manufacturers that you're considering, 2 car sizes, and 4 colors. How many different cars could you have chosen? So there were 3 manufacturers, 2 sizes, 4 colors. 3 times 2 times 4 is 24 different cars that you could have chosen. If we look at the tree diagram, that confirms our result of having 24 different cars to choose from. There are different types of probability. The first type we're looking at is known as classical or theoretic probability. In this case, each outcome needs to be equally likely. Now, if I asked you what's the probability of tossing a coin and having it land on heads, none of you need to pull out a coin and toss it over and over again to see what's going to happen. Classically or theoretically, we kind of know that the probability of tossing a coin and having it land on heads is 1/2. Because the number of outcomes in our event E divided by the total number of outcomes in the sample space gives us that probability. So for our example, the probability of tossing a coin and having it land on heads is 1 out of 2. Suppose you want to roll a six-sided die. Let's find the probability of each of these events. So our sample space consists of 6 different outcomes. The first one, the event of rolling a 3, 1 out of the 6. So the probability is 1/6 or 0.167. How about rolling a 7? Well, there's no 7s in the sample space. Thus, there's 0 events that match our outcome. And 0 divided by 6 is 0. And the probability of rolling a number less than 5. Well, the numbers less than 5 are 1, 2, 3, and 4. So 4 out of 6, or 0.667, is the probability of that event. Next, let's look at empirical, also known as statistical probability. In this case, we're going to need to absolutely base our probability on observations. We need to get out there and toss a coin. And we can find the probability of rolling a head by tossing a coin 1,000,000 times and seeing that we probably don't get exactly 500,000 heads, but we'll get close enough to it. We're going to see that theory in just a second. But it's based on the relative frequency of the event, which is the frequency of the event E divided by the total frequency of the number of times we do this experiment. There's certain things that we just don't know. If I asked you what's the probability of getting hit by lightning in the state of Florida, you would have to observe. You'd probably get on the internet and have to observe how many people got hit by lightning, the frequency of the event E, and the total frequency would be the population of Florida, and that would give you the probability of getting hit by lightning in the state of Florida done empirically. Now suppose, here's an example of empirical probability. Suppose this company does a telephone survey to ask people if they have a positive overall impression of the past decade. And they want to know what's the probability that a randomly selected person has a positive overall impression. Well, out of the 1,504 people surveyed, 406 had a positive outcome. Thus, the probability of finding someone with a positive outcome is 406 divided by 1,504, which is approximately 27%. The law of large numbers is what I was talking about a minute ago. If you toss a coin 2 times, even though we said the probability of tossing a coin and having it land on heads is 1/2, that does not mean that if you toss a coin exactly 2 times, you are going to get exactly 1 head and 1 tail. It's if you do it many, 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 many times that the probability starts approaching the actual or theoretic probability. The last type of probability we're going to look at is known as subjective probability. This is done with intuition or an educated guess. This is what the weatherman does when he says the probability of rain today is 30%. He's using his education to give us a good probability or subjective probability of the rain. A doctor may feel a patient has 90% chance of a full recovery. He's using his education to come up with that answer, so that is subjective. Now let's look at 3 different examples and see if you can figure out whether this is an example of a classical probability, an empirical probability, or subjective probability. The probability that you will get the flu this year is about 10%, 0.1. Well, that's probably done by a nurse or a doctor or someone with education. So it's done as an educated guess. So that's subjective probability. The probability that a voter chosen at random will be younger than 35 is 0.3 or about 30%. Now this we probably had to get online and figure out how many voters we have in our district and then count how many of them were younger than 35. So this was done by observing that number, thus it was done empirically. And last, the probability of winning a 1,000-ticket raffle with 1 ticket is 1 out of 1,000. None of us had to go out and buy a bunch of raffle tickets to figure this out and see how many we won and how many we lost. We did that classically or theoretically. And each of those tickets were equally likely to be winners, so that is a necessary condition for classical probability. Now the range of probabilities are always between 0 and 1 inclusive, where 0, a probability of 0 means the event is impossible to occur. The probability of 1 is the probability of the certain event. The 0.5, or the half, is equally likely. It's the heads or the tails. And as we go down from the 0.5 to 0, these are getting more and more unlikely. And as we go from 0.5 to the 1, we're getting events that are more and more and more likely. The complement of an event E is all of the outcomes in the sample space that are not E. So suppose we have our experiment is rolling a 6-sided die, and the event E isn't rolling an even number. So the 2, the 4, and the 6 are in the event E. Then what's left out? The 1, the 3, and the 5. So E complement consists of the outcomes 1, 3, 5. It's usually denoted with an E prime. And now the probability of E prime, E complement, plus the probability of E is certain to occur. All outcomes are either E or not E. And so it's certain to occur, so its probability is 1. If we know the probability of E complement, we can find the probability of E by subtracting it from 1, and vice versa. Suppose we have this sample of 1,000 employees, and we recorded the age, and we want to find the probability of choosing an employee who is not between 25 and 34. Well, we have 366 people who are between 25 and 34, so the probability that someone will be between the ages of 25 to 34 is 0.366. Thus, the probability by the complement rule is 1 minus 366 divided by 1,000, or 0.634. Suppose we have a probability experiment consisting of tossing a coin and then spinning the spinner. Let's find the probability of tossing a tail and spinning an odd number. Well, the tree diagram looks like this. So tossing a tail and getting an odd number consists of T1, T3, T5, and T7. And it's 4 out of 16, or 1/4. Let's use the fundamental counting principle to find a probability. Suppose your college ID consists of 8 digits, which can be any number between 0 and 9, and the digits can be repeated. Let's see what's the probability of someone guessing your ID number. Now, each digit can be repeated, and there are 10 choices for each of the 8 digits. Using the fundamental counting principle, there are 10 times 10 times 10, 10 ways to choose the first, 10 ways to choose the second number, 10 ways to choose the third number, and so forth. So we get 10 to the 8th, which is 100 million possible ID numbers. Well, your ID number is exactly one of those 100 million. So the probability of guessing your number is 1 out of 100 million. That's the end of section 3.1. Now go to the Course Compass website and do the homework for section 3.1.